These Scottish cows are right up there when it comes to keeping up with modern technology. They're equipped with connected fitness collars, which, along with other gadgets, not only improve their well-being, but the farmer's business too.
Dairy farming has been handed down from father to son for 3 generations here at Parkend Farm in Scotland. But keeping an eye on the cows has never been easier. On his smartphone, Brian receives automatic emails from the farm's computer system that alert him of any changes in the cow's health or fertility status. The data is collected by the collars the animals wear around their neck.
The collar indicates that there's been a drop in the cow's average eating time, or average rumination time, or average activity, and any one of these factors could be a primary indicator that the cow is either sick or is just starting to get sick. And the key fact behind these collars is they can pick up these problems before they become very serious problems.
When the animal eats, its neck muscles move. The movement is captured by the collar's sensors and wirelessly collected and processed. The collar's developers are planning to add location tracking, which would be particularly valuable for free grazing cows.
What's happened with the technology evolution over the last 10 years is that processing powers become cheaper, the energy spent in processing has become less, and the functionality has become, the form factor, the shape, form and size of it becomes much more manageable. It's only under those criteria that you could create an economic solution using technology for the farming sector.
Here, milking robots measure the volume and composition of the milk produced by each cow. Farmers use this data to boost productivity and improve the well-being of their animals. These and other smart innovations are being studied at 24 farms across Britain as part of a European research project aimed at making agriculture more sustainable and more efficient.
The first stage of it is to find the extent of issues, collect the data over the farm so we know what's going on the farm. Then we can identify the causes of inefficiencies on the farm. And once we know the causes, we can find the problems to solve those solutions.
Brian says that in the 6 months since he adopted the new technology, production has increased by 1/5 and the animal's health has improved too. Researchers see even greater potential in integrating sensor data along the production chain by developing a common standard for data exchange.
Where you will get a real impact and make life even more easier for Brian and his colleagues in the sector is to try and create a consistent and coherent database which takes both the data coming from an input collar system and an output robot system, and then you can match input to output.
Almeria in southern Spain, otherwise known as the Sea of Plastic. Tens of thousands of greenhouses that supply much of Europe with tomatoes, bell peppers and other vegetables. It is also a study site. This experimental greenhouse is rigged with sensors. The objective is to find out exactly how the plants are doing.
We're trying to simplify the acquisition of data for growers into one single cloud database. Then, using artificial intelligence and big data technology, we'll be able to reach certain conclusions for the entire region. And this will allow us to compare and further improve the way the product is grown.
Soil moisture, plant growth, the composition of the air inside the greenhouse and other indicators are measured to help farmers grow better products while optimizing irrigation and the use of fertilizers. On a large scale, smart farming has substantial economic benefits for the producers.
The Internet of Things and the sensors and all the information, all the data that we're gathering can be aggregated at certain levels, fed into the cooperatives, and used to give feedback so that they can have a much better sense of their processes of production, their efficiencies, their water use, the amount of labor that they put in, whether it's market information, are they producing the right varieties, etc., etc.
Once the tomatoes are picked, the data harvesting continues. 2 million kilos of tomatoes are processed in this sorting facility every day, and the bulk of the work is done by machines. Pictures are taken of each tomato, which is then automatically sorted by size, color, and even taste.
There's no doubt that this kind of technology gives us a competitive advantage. This facility is possibly the most advanced in Europe at the moment. As you can see, there are very few people working here. All the manual selection processes, which are expensive and complicated, have been reduced to a minimum.
Researchers are working on gathering all the information, from greenhouse to processing, into one single database. This would provide traceability from farm to store, increasing food security and making the whole chain more efficient.
The farmer would get information about the products he's shipped, the processing companies could get information about the products they're receiving, and the consumer would get information on the entire food value chain.
There are plenty of other uses for sensors, including below the sea. What is, for example, the fastest and most reliable way to measure water pollution? We're off to southern England, where researchers are testing a new mini laboratory to analyse water.
Urban and rural waste often ends up in bodies of water which get contaminated with excessive nutrients, particularly nitrogen and phosphorus. To protect underwater ecosystems, communities are taking measures to try and limit that pollution. The problem is the concentration of nutrients varies throughout the day. Onshore laboratories can't measure the changes in real time. So the solution is for the labs to go underwater.
Rather than taking a sample and analysing it in the laboratory, we can leave the sensor deployed in situ for long periods, and it can take a measurement every 15 minutes and collect really long data sets, giving us some very high resolution data, which allows us to pick up some of the trends that would not be visible if we were just taking samples periodically.
This device is called a lab-on-a-chip. It's a relatively compact and inexpensive system that integrates various laboratory functions and is easy to use. The goal being for non-specialists at wastewater treatment facilities, or even ordinary citizens, to be able to take measurements and control water quality.
We did a bit of a combination. We created sensors individually, but then combined them together. The idea is we would create a multi-parameter sensor. So we could look at nutrients and temperature and pH and salinity all at the same time to give us a more holistic view of what was happening in the environment.
The lab-on-a-chip is based on a plastic plate tunneled with complex pathways for liquid reagents. Optical sensors are added to spot color changes that indicate the presence of particular substances in the water. The chemicals are all safely stored inside the device.
This system is designed to go to the bottom of the ocean, so we've deployed them to about 5,000 meters, and they should be able to go to 6,000 meters, and we've tested them here in the pressure test facility down to 6,000 meters.
The researchers are working with private companies to improve the sensors in terms of functionality, cost and size, like this commercially available fluorometer that measures hydrocarbons contained in water using the fluorescence of organic molecules.
One of the aims within the project was to take what is a wide range of sensors and narrow it down to a single design that could cover all of our applications, making it much easier to manage in manufacturing.
Simplifying manufacturing, that's the challenge. This manufacturer in the Danish university city of Aarhus produces extremely accurate microsensors used by researchers all around the world. Each sensor is made by hand from a glass tube. The opening must only be a few microns wide. A meticulous job that requires a steady hand and a lot of patience.
I can make maybe 20 a week. That works. Of the standard one. Yeah. an oxygen sensor is a standard sensor, so they are the most easy ones to make.
The oxygen molecules pass into the tiny opening through a membrane and interact with a thin platinum wire, producing a weak current that can be measured. Such microsensors are used in a variety of fields, from blood analysis to pollution and greenhouse gas emission control.
For a lot of industrial applications, there could be a huge demand. A very good example is the nitrous oxide sensor that can control how much nitrous oxide that is being emitted from wastewater treatment. And it's still based on the same principle. It's still micro size inside, but they can be made more sturdy, so they can be placed in the wastewater treatment plant. And there, the market in principle is enormous.
To meet this expected demand, developers are working on new mass production methods to replace the glass with plastic, which would increase the microsensors' longevity by making them more resilient and eventually more affordable.
When we compare the two sensors here, internally they have the same dimensions. The membrane is the same size, the amount of the number of molecules that passes over the membranes are comparable, but they are constructed in a very different way on the outside. And this is mainly to achieve robustness. And of course we can produce this at a different price than this one, because this one is handmade.
From greenhouses to the bottom of the seas, these innovative technologies not only help better understand our world, but also boost productivity, as well as the debate such enhanced production generates.